Let's look at evaluating an integral by interpreting the areas involved in these integrals. So for example, here we have the integral of the square root of 1 minus x squared from 0 to 1. Here is the graph of the square root of 1 minus x squared. We can see it's a quarter of a circle. Now we're only looking for the area of this quarter of the circle because we're looking on the interval 0 to 1. Well, we know that the area of a circle is pi r squared, where r is the radius. And for this circle, the radius is 1. So if we were looking at the area for this entire circle, it would be pi times r, or just pi. Now, since we only want a quarter of the circle, the area under this quarter of the circle would be pi divided by 4. Now, looking at the area for this line, x minus 1 from 0 to 3, we're going to have to look at the net area. So looking at the net area, we are going to have to be looking at the area here, which would be a negative area, but we can find that because we know the area of a triangle is 1/2 base times height. And so our base would be 1, and our height is, let's see, each one of these is half a unit, so our height would also be 1. I know that goes down to -1, but we're looking for that distance. So this area right in here would have a -1/2 value. Now we're going to add the positive area. So we're just going from 0 to 3, so we need to go to here just to find this area. So again, we know we have 1/2 base times height, and this is our base from 1 to 3, so that's a length of 2. And then the height is from here to here, which is also 2. So we have 2 minus 1/2, which gives us 3/2. So this integral equals 3/2, and this integral we said equals pi over 4. Just by interpreting the areas, since we understand that this expression here represents the area under the curve for this graph from 0 to 1, and that's a quarter of a circle, pi fourths. And likewise for this one, we're looking for the area under the curve of x minus 1, but it's going to be net area since part of it is below the x-axis. And so we just combine those two to get 3/2. The midpoint rule. Now there's an advantage to using the midpoint when we're using our Riemann sums. And that advantage is that if we think about finding the area under the curve of this function from A to, let's say, B, and instead of using the right side or the left side of the function, we use the midpoint. Now the midpoint of the rectangle, you can see it kind of averages out the over and under estimate many times. So here's the midpoint. So the rectangle is going to go through there. Here's the midpoint of the next interval, so the rectangle would go through there. So you can see, here we have a little overestimate, but here it's an underestimate, and they seem to balance off a little bit. So the midpoint can give us a little bit better of an estimate when we're estimating the area under the curve using our Riemann sums. Now, we're going to find our delta x the exact same way. That's the width of our rectangles. However, in order to find these midpoint values, we're going to take the interval and divide it by a half. So we would take this value here, our x sub I and our x sub I minus 1, add those together and divide by 2. That will give us the midpoint of that interval. So that's how we find the midpoint of an interval. And then we can use our Riemann sum to do the calculation with the midpoint of the rectangle. So here's an example. Use the midpoint rule with n equals 5 to approximate this integral. Now, if we're looking at this interval from 1 to 2, and we're using the midpoint, let's show where these values come from. So if I have 1 over x, it may look something like this, from 1 to 2. We're looking for the area under the curve here. Now, we're letting n equal 5, so we're breaking this up into 5 equal intervals, or the width of each rectangle, delta x, would be 2 minus 1 all divided by 5, or 1/5. So the first rectangle, since the width of each rectangle is 1/5, this value right here would be 1 plus 1/5. Now, if we converted this to tenths, we'd say this is 2/10, or 1.2. So this would be 1.2. But we want the midpoint of that interval, because we're going to be using the middle of the rectangle. So do you see that we would take 1.2 plus 1 divided by 2, and that gives us 1.1. That would be the value we plug in to get the midpoint. That's where we get 1.1. Now the next interval, this would be 1.3. No, let me erase that. We would, since each rectangle has a width of 1/5, we'd have one. I'm going to take this value right here, this 1.2, 1.2, and add 1/5, which we said is 0.2. So that would be 1.4. Now, to find the middle of that interval, we would take 1.4 plus 1.2 divided by 2, and that would give us 1.3. So that is the value that we're going to plug in for the height of the second rectangle. So that's how we're going to use our midpoints for the height of the rectangle. So we said the width of each rectangle is 1/5, and then we saw these values, where these values 1.1, 1.3, that we're plugging into the function, where those came from. And we're using 5 rectangles. So we have 1, 2, 3, 4, all the way up to f of 1.9, our 5th rectangle. So that would be an estimate for the area under the curve of 1 over x from 1 to 2. And if that was a little fast, if we looked at that area, we get 0.691. So that would be the approximation for the area under the curve of 1 over x from 1 to 2. This is just the graphical representation of the midpoint, how we found those values to plug into the function. So we got the height of the rectangle at its midpoint of that interval. Let's look at some properties of definite integrals. The first one, if we look at the integral from a to, or b to a of f of x dx, that's equivalent to taking the negative and then switching our upper and lower limits of integration. So that's one property. The next one, if we take the integral of a function from a to a, well, there's not going to be any width to our rectangles, or there's not going to be any width to the area, so we're not going to have any area. So that would equal 0. The next one, if we looked at our function here, our function that we're working with would be f of x equals c, a constant. So we would just have a constant function, y equals c, and we're looking for the area under the curve from a to b. So we are just looking for this area. Well, if we want to find the area of a rectangle, we know this length right here is just b minus a. This length here is just c. So to find the area, we'd have c times b minus a. This one, we can see that if we're taking the integral of an f of x plus a g of x, we can break that up and take the integral of f of x from a to b and add it to the integral of g of x from a to b and get the same result. And likewise for subtraction, we could do the same thing with subtraction. This integral indicates that if we're multiplying our f of x times some c, some coefficient, some number c, we can take that out in front of the integral, find the integral of f of x from a to b, and then multiply by c. That's only if c is a constant. And this one is like number 2 above, only it's subtraction instead of addition. Use the properties of integrals to evaluate this integral. Okay, our solution. We can break this up using the properties we just saw. And then we could actually rewrite 3x squared by bringing the 3 out front. Now applying some more of the properties, we know that if we are taking the integral of 4 from 0 to 1, remember that's a constant function, y equals 4, and if we're looking at the area under the curve from 0 to 1, we would just have 4 times 1. So that equals 4. And we evaluated the other integral earlier, the x squared from 0 to 1, and we got 1/3. Now, if we take the integral of x squared from 0 to 1, which is 1/3, we now can multiply that by 3. So we would get 3 times 1/3, which is 1. So we'd have 4 plus 1 is 5. Another property. Let's look at this property graphically. If I have some function and I'm looking at this first integral here, if I'm looking at finding the area under the curve from a to c, this would be this first integral here. Now the second integral, I'm looking at the area under the curve from C to B. So do you see how these added together would be equivalent to finding the area under the curve from A to B? Now this comes in handy sometimes when we're working with absolute value functions. Because here, if I'm looking for the area under the curve from A to B, well, I'm going to break it up at C because I'm going to find the area under the curve from A to C because this function representing this piece of my absolute value is going to be different than this function. So I would then add from C to B, and then I would take this function here. Because remember, these absolute values can be represented as a piecewise function. And then we could just add those together to find the total area under the curve. That's how we could use this property. Okay, here's a problem for us to solve. If the integral of f of x dx from 0 to 10 equals 17, and the integral of f of x dx from 0 to 8 equals 12, find the integral of f of x from 8 to 10. So if we have some function and we know the area under the curve from here to here, we know the area under the curve, oops, this is 0 here. From 0 to 10, we know this area is 17 from here to here. This area is 17 under the curve. Now it says from 0 to 8, the area under the curve from 0 to 8 is 12. So it's asking us to find the area under the curve from 8 to 10. So we need to find this area under the curve here. Well, we can see that if this whole area from here to here is 17, and we subtract off this area here, which is 12, that would leave an area of 5 for the remaining portion. Comparison properties for integrals. If f of x is greater than 0 for some interval a to b, then the integral of f of x dx on the interval a to b is greater than 0. Now I'm going to show maybe two of these, and then we'll look at them graphically. If f of x is greater than g of x on an interval, then the integral of f of x dx from a to b is greater than the integral of g of x dx from a to b. Let's take a look at those. Now the first one, if f of x is greater than 0, it just means the curve is above the x-axis. So if we look at taking the area under the curve, this is saying then this area has to be greater than 0. Since our curve is above the x-axis, we would get a positive area. The next one is indicating if f of x, say I have a function f of x here, and I have another function g of x, and we are looking at an interval from A to B, it says the area under the curve of f of x, the area here, that's the area under f of x, would be greater than or equal to the area under the curve of g of x. Here's the area under the curve of g of x. Since f of x in my example is greater than g of x, the area is going to be greater. Now it does say if f of x is greater than or equal to. So if they were equal to each other, then the areas would be equal to each other. Okay, looking at this one graphically. If m is f of x is greater than some value m, little m, so let's draw a graph here. So we have some value of m. Here's our function. So we have some value of m. That's kind of getting a little sloppy. Let me redo this. Okay, so we have some function on an interval a to b. So let's say this is a and this is b. Now f of x is greater than some value m. Now I'm looking at the smallest value on this interval would be here. So this would be m. And the greatest value on this interval would be here. So I'm going to call this big M. So do you see my function is between little m and big M on this entire interval a to b. And here a is going, yeah, I missed a little bit there, but there's a. It says m times b minus a is less than or equal to the area under the curve. Well, let's look at the area of m times b minus a. B minus a just is the length of this interval. And then m is this height right here. So we are simply looking at the area of this rectangle right here. We're looking at the area of this rectangle. So that would be this rectangle for this piece. Now if we looked at the next piece, this represents the area under our curve from A to B. So that would be this area here. And then the last piece is this rectangle. We go all the way up to big M, and B minus A is the length of our interval. So that would represent this area. So we can see that this area is between this area and this area. Estimate the value of the square root of x, the integral of the square root of x from 1 to 4. Well, if we're going to use just an estimate, we know that the square root function looks like this. And if we're looking for the area under the curve from 1 to 4, I can see that the area from 1 to 4 of the square root of x dx would be less than, now I'm looking for the maximum value on the interval. If I plugged 4 in to the function, we would get the square root of 4 times, now the length of this interval, see this here is the square root of 4, which that would give us 2. And the length of our interval is 4 minus 1. So we'd have 3 times 2 is 6. Now I'm going to look for the minimum on this interval, which would be here. So I know that if I created this rectangle here, this would have a height of 1, and the length of the interval is 4 minus 1. So this would be 3. So I know the area under the curve has to be between 3 and 6. So that would be an estimate for the value of the integral of the square root of x from 1 to 4. And there's a graphical representation of the smaller rectangle, the larger rectangle, and the area under the curve would have to be between those two values.